Okay, so let's begin. So the second speaker of this session is Netta Engelhardt from MIT, and she's going to tell us about the simple models of evaporating black holes. Please.
Thank you, Rosie, and thank you to all the organizers of the conference, especially for plowing through in a time of pandemic and still giving us a Strings 2020. It is really good to see so many familiar faces. I really hope that everyone is doing as well as can be hoped in the current difficult time. So my talk today is on models of black hole evaporation, specifically for ADS black holes. And this is, of course, part of a larger effort to that's been going on for a long time to try to understand the black hole information paradox better using ADS CFT. So, sorry. Now here I've drawn a picture actually of a non-ADS black hole, an evaporating asymptotically flat black hole with two Cauchy slices, a spatial slice sigma and a spatial slice sigma prime. And of course, the canonical problem is what Hawking showed, that it appears that there is evolution from a pure state to a mixed state, which is in contradiction of unitarity. Now, I think most of us in this Zoom room will probably agree that quantum gravity is a unitary theory, but it takes more to resolve the information paradox than just all of us sitting down agreeing that everything is unitary at the end of the day. We really need to have an understanding of the detailed dynamics via which information actually gets out in their radiation. So one diagnostic that has been used traditionally is the von Neumann entropy of the radiation, minus trace rho log rho, where rho rad here is the state of the Hawking radiation. And this is traditionally served as a diagnostic for information loss or information conservation via what we call the page curve, which is just the curve, the dependence of the entropy as a function of time. So here I've drawn the two systems in the problem, the black hole and the radiation, and this is just the usual picture you see of the page curve where we have the entropy of the black hole, which is measured by the area of the black hole over 4gh bar. So this is just the Bekenstein-Hawking entropy, and the entropy of the radiation as measured by minus trace rho log rho and as computed by Hawking. Now the black hole entropy is decreasing because the area of the black hole decreases due to Hawking radiation. And the entropy of the radiation as computed by Hawking increases until it eventually saturates up here on the top. So this is what the non-unitary evolution would look like. In the unitary case, we would expect that eventually the radiation begins to purify itself and that it ends up in a pure state. So it would look non-monotonic, something like this. And so this picture, this unitary curve, we often think of as a diagnostic tool or litmus test for unitarity. Now, a computation of the page curve by itself, I should say, it doesn't amount to a resolution of the information paradox. The page curve is not a panacea for all of our problems about the information paradox. The resolution of the full resolution of the information problem would require, as I said before, a fine-grained understanding of the state of the radiation and the dynamics of the system. Nevertheless, a direct calculation of the page curve is in fact a large step forward. Now, one of the reasons that I would say we didn't really distinguish between computation of the page curve versus the resolution of the information paradox until now, or until recently, is that we simply did not think that it was possible to calculate the page curve using the tools at our disposal. In particular, there was an expectation that this type of calculation, the calculation of the page curve, would simply require this fine-grained understanding of the state, of the dynamics of the system, this extensive knowledge of non-perturbative quantum gravity physics. And so we sort of lumped them in together with the things that we don't know how to do. And this was indeed not the case at the end of the day. So the new developments, and I use new as a way of referring to what's been happening for the past little over a year. So these new developments that started in May 2019 and are still unfolding, these have appended the idea that the page curve for unitary black hole evaporation can actually be calculated with no direct input from non-perturbative quantum gravity physics. So this is something that I believe will be reviewed in more detail in the review session on Friday. I am going to need some of this for my talk, so I will review some aspects and hope that, and I will try not to go into too much of the details because I believe this will be reviewed and discussed also later in the week. Now, I said here there's no direct input from non-perturbative quantum gravity physics, and I was pretty careful to say direct. And that's because the calculation itself, especially the one that was done in May, is semi-classical but heavily motivated by holography. The interpretation of the calculation is motivated by holography, and the later developments use the gravitational path integral instead. So today, what I'm going to do is discuss first the original setup from May. And in that setup, you have a semi-classical analysis of an evaporating ADS black hole. And if you just, the only thing you have to put in is holography, and you get a unitary page curve. I'm also going to describe a newer model of black hole evaporation that exchanges this semi-classical analysis for a purely classical analysis at the cost of dynamical topology change. Now you might ask why we want to do that. And the answer is that it turns out that there's actually a fair amount of benefit to a simpler model which has in very clear detail a certain type of quantum gravity dynamics. So, and I'll discuss how that helps us understand certain things. One upshot of both of these two simple models of ADS black hole evaporation, as well as some of the more recent developments on replica wormholes, is that we really want to get a better understanding of the mechanism behind the surprisingly smart gravitational path integral. So I am going to briefly advertise some upcoming work. It's just going to be a teaser trailer. This is work with Alex Milne and Sebastian Fischetti that hopefully will appear in the archive in the next couple of weeks on the calculation of free energy from gravitational path integral, where the replica wormholes actually play a pretty critical role. So this will be at the end of the talk. Hopefully I will have time to discuss it. And so without further ado, let me begin with a semi-classical model of ADS black hole evaporation, and later I will talk about a somewhat classical model of ADS black hole evaporation. So in talking about evaporating ADS black holes, we have to face a very familiar problem in physics, which is conservation of misery. If we have a black hole, which is an ADS black hole, which is large enough that it doesn't, that we can understand it well, it doesn't evaporate. And conversely, if it's small enough to evaporate, we don't really understand it. So how do we get around this problem? And the qualitative answer is that we actually are going to force an ADS black hole to evaporate by coupling it to an external reservoir, which is cooler. So this is what a black hole looks like before evaporation. We have this is a two-sided black hole. We have a left side and a right side, and there's a bifurcation surface between the two. The bifurcation surface is the same for the left and right boundaries. And so this is the behavior before evaporation. Now, in order to force this black hole to evaporate, we are going to take an auxiliary system, a bath, a reservoir, whatever you'd like to call it, and we're going to couple it to the bulk, and then allow for we have transparent boundary conditions to allow for exchange between the two, which allows the black hole to evaporate into the bath. So we're going to, what we did, we worked in a setting where we can do the calculations directly, which is the particular case of JT gravity coupled to a bulk CFT. So here we have a CFT living in this two-dimensional ADS2 bulk. But Jeff Pennington showed similar results in higher dimensions if you assume spherical symmetry. So very qualitatively, how do we evaporate this black hole? So I'm going to take the bulk CFT to be the Poincare vacuum. And to evaporate the black hole, we're going to consider an auxiliary BCFT in flat space at 0 temperature. And so the way we do this is we couple the two systems at physical time u in the ADS2, and which is the time u in the Minkowski space. And then there's the effect of coupling results in a quantum quench, which has a shockwave propagating into the bulk. And after that, we evolve the two systems forward. And as a consequence of that, we are allowing our black hole to evaporate. Or in some, you could say we are forcing it to evaporate. So now we have an evaporating black hole in ADS, and we are ready to compute entanglement entropies in order to see what kind of page curve we get. Now, of course, if we just calculate minus trace rho log rho the way that Hawking did, then we're not actually going to get anything different from what he got, because it's not that this ADS black hole is so qualitatively different that if we do the same calculation, we're going to get some kind of a novel new unitary answer. We need a different ingredient here, which is, of course, holography. That's the main reason that we wanted to work with an ADS black hole in the first place. And so instead of using the Hawking version of the calculation, we're going to use a holographic prescription for computing entanglement entropy. So how do we compute entanglement entropy holographically? Well, if we're working to first order in GH bar, which is to say we're working not including the back reaction of quantum fields on our geometry, then we have the so-called HRT or FLM proposal, which tells us that if you want to compute the von Neumann entropy of a boundary state rho sub R here can be either a subregion if you're in higher dimensions, or it can be the full boundary, it can be multiple boundaries. If you want to compute this, then you have to look for an area, for a surface, x sub R, which is the minimal area surface that extremizes the area. Meaning, if you consider arbitrarily small deformations of XR, then its area is stationary to first order. So in the two-dimensional case, instead of area, we take the dilaton. This is an extremal surface. It has to be homologous to R. And we pick the minimal one if we have multiple ones. So you pick the surface, and if you want to compute to first order in GH bar, but including the correction from quantum fields, but not including their back reaction, you also include the von Neumann entropy of the bulk fields on one side of the surface. Now this works extremely well if you're working to leading order in GH bar. But once you want to include quantum corrections, back reaction of quantum fields on the geometry, then you run into the situation where various consistency conditions can actually be violated by this proposal. So for example, strong subadditivity inequality, you can run into problems with various other consistency conditions such as entanglement wedge nesting and causal wedge inclusion. Now, it's actually quite a familiar problem if you think a little bit further back from the 1970s, where there was a similar issue in including, in modifying a prescription that used area to include for quantum back reaction. So this very similar problem occurs in black hole thermodynamics. So in black hole thermodynamics, we normally think of the Hawking area theorem as the second law of thermodynamics. But as I just mentioned a few slides ago, in an evaporating black hole, the area decreases as a function of time. And I suppose to quote Sir Arthur Eddington, if your theory fails the second law of thermodynamics, I can give it no hope. There is nothing for it but to collapse in deepest humiliation. So to avoid the collapse of general relativity in deepest humiliation, no less, Jacob Bekenstein proposed that instead of just taking the area as a statement, the area increases the statement of the second law, you replace it with a quantum corrected area, which is this generalized entropy. So the generalized entropy is the area. So sigma here is meant to be a cross section of the event horizon. And I've drawn here a spatial slice. So sigma divides the spatial slice into two. There is the interior of the black hole and the exterior, in and out. And the generalized entropy is the area of sigma over 4GH bar plus the von Neumann entropy outside of sigma. So on this one side of sigma, which is outside the black hole. And this is what he proposed increases as a function of time. And since this quantity has since been studied, one could say almost ad infinitum, there is a large body of evidence that indicates that S-gen is most likely UV finite. So it's a very nice quantity. And so this, we can take lessons from this problem that occurred in black hole thermodynamics in the early 1970s and was resolved by replacing area with generalized entropy to do the same thing for our entanglement entropy, holographic entanglement entropy proposal. And so recall in the original proposal, you were computing the area plus entropy of a surface that was defined as the extremum of the area functional. To generalize to all orders in GH bar, we still compute, you could say, the same quantity, this area over 4GH bar plus von Neumann entropy, this generalized entropy. But the way we do this is not by looking at the area the surface that extremizes the area, but rather the surface that extremizes the generalized entropy. So this is a different surface. It extremizes instead area over 4GH bar plus S out. And that's what I call this chi-R over here. If you have multiple such surfaces, you take the minimal generalized entropy surface. So here is an illustration. This is a Cauchy slice here. And in a higher dimensional system, we have this, we can split the boundary into multiple subregions. This is a region R. And here is a quantum extremal surface. It splits it into in and out, and we compute the area for GH bar of this, plus the von Neumann entropy on one side of it. So this is the quantum extremal surface prescription that allows us to compute holographic entanglement entropy to any order in GH bar. Okay, so now we're armed with an evaporating ADS black hole and a prescription for computing the von Neumann entropy. And I should say, if you were worried about consistency conditions that I mentioned in the last slide or 2 slides ago, this prescription does satisfy those under a fairly mild assumption about what the quantum fields are doing, known as the quantum focusing conjecture. Let me make one brief comment, which will turn out to be relatively important, on complementary recovery. If we have a system in a pure state, so if we have a bulk system in a pure state or a bulk plus bath, as say, in a pure state, then the quantum and also classical extremal surface of a subsystem R is going to be identical to the quantum extremal surface of its complement. So in particular, if the bulk state is mixed, which is going to be the case in our evaporating ADS black hole, that means there's an additional system that purifies the bulk. And so if R is a subset of the boundary and R bar is the complement on the boundary, then it must be the case that chi R is not the same as chi R bar because we have an additional system, the purifier. In particular, this means you can have a situation in which a surface is quantum extremal with respect to one side, but not quantum extremal with respect to the other. It's easy to see this if you just consider the fact that if this is not a pure state here, then if you evaluate the von Neumann entropy of this on this side, it will not be equal to the von Neumann entropy on the other side. So this is an aside that will turn out to be fairly important in just a little bit. Okay, so now we have our quantum extremal surface prescription. We have our evaporating ADS black hole. Let's go ahead and put this to work. So initially, when we evaporate the black hole, the quantum extremal surface of the right side moves continuously in a space-like direction. And so that's what is going on down here. But eventually, at late times, there is a branch of quantum extremal surfaces that are not anywhere close to a classical extremal surface, and that begins to dominate. So that is what this surface over here is doing at late times. And in particular, after this transition, this exchange of dominance, the dominant right quantum extremal surface is far from a left quantum extremal surface. And in fact, it is a right quantum extremal surface and not a left quantum extremal surface. It is not quantum extremal with respect to this side. The effect of this transition in dominance is actually the unitarity of the page curve. So that you get this quantum extremal surface, this new one, is responsible for the downward leg of the page curve. Now, here is an interesting comment, which is based on the earlier slide on complementary recovery. So we now have 3 systems. We have the left boundary, the right boundary, and the purifier system. And we have these 2 entanglement wedges, the right entanglement wedge and the left entanglement wedge. And then we have this gap between these 2. And so the hypothesis that was made most explicitly in this paper by Allenheimer, Mahajan, Maldacena, and Zhao, is that the gap between these 2 surfaces belongs in the entanglement wedge of the purifier. This is the so-called quantum extremal island that has been making headlines. Now, the existence of this gap is synonymous with the bulk state being mixed. There's a purifier system, the bath, that purifies the left and right boundaries. So imagine we could take the bath and we could throw it into the left boundary, and then the left quantum extremal surface would move so that we would not have a gap any longer. And again, this gap is the so-called the quantum extremal surface, the quantum extremal island. So a few points of discussion and what we can take away from this. So one upshot of these papers from May is that semi-classical calculations by themselves, if you just use semi-classical tools, you can get a unitary page curve. Now, since then, there have been, of course, a lot of developments. And in the more recent results of what has become the East and West Coast papers, I believe that's the correct way of referring to them these days, these results, these semi-classical calculations can be justified, at least in certain models, without invoking holography, instead using the Euclidean path integral, the gravitational path integral, and including Euclidean wormholes. And I believe there will be a lot of discussion on this on Friday. But we still don't have a complete understanding of what's going on. So for example, here's something that we don't understand. Our system can be the low energy effective theory of both unitary and non-unitary UV completions in principle. And clearly, this calculation above that we just did correctly computes the entropy only for the unitary theory. But of course, we're working in a low energy effective theory, so how does it know? How did it know that we are computing something for the unitary UV completion, not for a non-unitary one? In particular, what if the quantum extremal surface prescription is just an automaton that spits out a unitary answer, no matter whether the UV completion is unitary or not? It's not a very good prescription if that's what it does. If no matter what kind of quantum gravity theory you feed it, it always gives you a unitary answer. So one way of trying to answer this question of whether the quantum extremal surface prescription is actually sensitive somehow to details of the UV completion is if we had a holographic non-unitary theory. And then we could ask, would quantum extremal surfaces give us the correct answer in this case, which in this case would indeed be a lack of unitarity? It's actually very difficult to see in this semi-classical model. So a simpler model would be very nice. And what could be simpler than a semi-classical picture? A fully classical picture. So there's an example of a fully classical picture in this paper by Ahmed, Raghu, Huan, and Ying, which gave a 3D holographic interpretation of this calculation. We're going to look at a different model, which has very explicit quantum gravity dynamics that we can then look at. So that'll make it easier to test whether this quantum extremal surface prescription is actually giving us the correct interpretation, the correct answer for a given quantum theory of gravity. And this brings me to a somewhat classical model of ADS black hole evaporation, which is based on work with Chris Akers and Daniel Harlan. So let's work with a toy model. So the main plus of this toy model is that the dynamics of quantum gravity will be quite explicit. We have a black hole, and it's going to evaporate by the emission of smaller black holes. And this is our model. This is just a stand-in for the Hawking quanta. So the emission of a black hole, the way that we're going to model it, results in a wormhole from the original black hole with a new exit. And I'll have a figure of that on the next slide. And I should say this is inspired by ER equals EPR. So there you would imagine having these quantum wormholes. This is just can be thought of as a classical version of this quantum octopus. Now, in ADS3 in particular, we can build these multi-boundary wormholes in a very explicit way by doing different quotients of ADS3. So in order to be fully explicit with our construction, we're going to be working within ADS3. So what are the dynamics of this model? We're going to consider discrete time steps, which will bring a topology change. So here we have our smiling, happy ADS black hole, which is evaporating. It has multiple exits. So this has already evaporated 3 Hawking quanta. Each of these represents one of these Hawking quanta. This is the Hawking radiation, and we're modeling it as holographic. So this is one time step, and these are the bifurcation surfaces. So each one of these is a constant time slice. It's a totally geodesic slice. And then we have this admittedly ad hoc time evolution in which the next black hole has now evaporated one more Hawking quantum. And as a consequence of that, we have our alien needs to get a new pair of pants. So now we have 4 exits to the wormhole, and afterwards we have 5 exits to in this wormhole. And again, this is really inspired by ER equals EPR. It's just a classical caricature of the quantum octopus. So what is going on here in terms of the page curve, in terms of the quantum extremal surfaces, or in this case, just classical extremal surfaces, and this is purely classical. Well, at early times, we have very few of these exits. So the minimal area surface is just gamma. That's the bifurcation surface of the Hawking radiation. Now, when I say gamma, I should be clear. When I say gamma, I mean the gamma is the union of all of these little exits over here. I believe Daniel calls these the ankle bracelets, so I will adopt the same terminology. So at early times, the ankle bracelets that are the minimal area surface. We have 2 candidates for the minimal area surface here. There is the extremal surface. These are both extremal, but this one at this stage has smaller area. Now, as we move forwards, this one here, again, this one here might have a smaller area than this one, but eventually, as the black hole evaporates more and more, there will be a switchover where gamma prime will now have smaller area than the area of all of these gammas together. And at that point, there is a phase transition, and gamma prime begins to dominate. And so what happens is initially the entanglement wedge of the black hole is quite large. It's everything up to these gammas. And eventually, after the transition, the entanglement wedge of the black hole is very small. It's just this gamma, everything between gamma prime and the boundary over there. So this is actually quite similar to what we saw in the semi-classical model, where the surface moved from where it was in the original bifurcation surface, or XL remains, to this new dominating quantum extremal surface after the page time. So what happens over there is, again, we lose a chunk of the bulk in doing this. And that's completely analogous to what happens here, where we go from having this very large amount of the bulk in the entanglement wedge of the black hole to a very small amount of the bulk in the entanglement wedge of the black hole as a consequence of this evaporation process. So there you get a page curve for this toy model. Initially the entropy increases, and then once there's a turnover due to exchange of dominance of the quantum extremal surfaces, the entropy decreases until the end, until the black hole evaporates altogether. So there is in fact an island also in this model here, and it has the nice advantage in that a lot of things are much more explicit because we don't have to worry about bulk entanglement. So the island in this model is just the region between gamma and gamma prime, just like before it was the region between XL and XR. So a nice aspect of this model is that this island phenomenon doesn't seem quite as mysterious. It's really just quantum error correction. So how do we see this? Very qualitatively. Let's imagine that we are maybe in this late time stage over here, and we want to recover something inside the island between gamma and gamma prime. If we pick too few of the radiation CFTs, too few of these, say maybe only 2 of them, then the entanglement wedge is quite small and does not contain the island. If we include a critical number of the radiation CFTs, or say maybe we include the black hole CFT, then we can recover. We can reconstruct what we wanted to. So the island is regained. And this sounds essentially identical to the story that has been told for a few years now about ADS-CFT as a quantum error correcting code. It appears that the island is essentially being included in this quantum error correcting feature of ADS-CFT. So before I go into the next slide of information loss, I'm going to begin with a disclaimer. We don't subscribe to information loss. We are not proponents of information loss. And the sole purpose of having a slide or several slides on information loss is to showcase what would happen if we did have a quantum theory of gravity with information loss. What kind of transition, what kind of features would the quantum extremal surface have? And would it give us the correct answer, which in such a theory is indeed non-unitary evolution? And to emphasize how much we don't subscribe to information loss, you will notice that there are smiley faces on these lovely wormholes which conserve information, but there are no smiley faces on the information loss model. So this is just to remind you that this is really an academic debate here. Now, what would a holographic calculation of information loss, what would a quantum gravity picture of information loss analogous to this dynamical topology change look like? So here we have one such possible model. We have, again, a black hole when it's, again, emits these small black holes as in lieu of Hawking radiation. But instead of there being a wormhole between the Hawking radiation and the black hole, now the Hawking radiation has a wormhole to something else, which we're calling the baby universe. This isn't strictly speaking a baby universe because it has an additional boundary, simply because it's simpler to have everything be holographic and modeled in terms of CFTs. So you can think of this as some kind of a stand-in for the baby universe. And with every time step, you get one more of these wormholes between the Hawking radiation and the baby universe. Now, what answer do we get for the page curve? What kind of entropy time dependence do we have here? Well, I've drawn the surface gamma prime for the black hole. But gamma prime is actually completely irrelevant for the Hawking radiation. It is not homologous to these boundaries, which means that it never features in any holographic calculation of the von Neumann entropy. The only extremal surface that matters for the Hawking radiation is this one right here. So the union of these. And so it's very easy to see here that as the black hole emits more and more of these smaller black holes as Hawking quanta, what happens is that you get more and more of these black holes and more and more of these gammas. And there is never any switchover because gamma prime never competes with gamma. And so what you get is simply an increase in the entropy until the black hole has finished evaporating, at which point it saturates. This is exactly the Hawking calculation. And so this is a model in which a non-unitary quantum theory of gravity would indeed have a quantum extremal surface, or in this case, a classical extremal surface prescription that gives you the right answer. Now, this is heartening that the quantum extremal surface prescription, or the more generally holographic entanglement entropy, is giving us the correct answer regardless of what the fine-grained dynamics are. And of course, let me reiterate, in case it wasn't clear the first 2 or 3 times I said it, we don't really think information is lost in a realistic quantum theory of gravity. But nonetheless, this academic exercise is very useful for understanding, for example, what type of thing Hawking was calculated and in what theory would that be correct. Now, a final comparison here between the happy information conservation picture and the less happy information loss picture. In the top picture, if suppose those are the dynamics we had, we might have said that the wrong Hawking calculation simply corresponds to using the wrong quantum extremal surface. So what do I mean by that? I mean that instead of using gamma until the switchover and then switching to gamma prime, we just use gamma always. And even past a point where gamma is no longer dominant in the sense that it has larger area than gamma prime. This would give us an answer that's completely analogous to what Hawking got. By contrast, in this bottom picture, if that were the correct dynamics, then we would have said that the wrong calculation would be to, at some point, start using gamma prime instead of gamma. Now, if we started using gamma prime instead of gamma, we could get a unitary answer. But it's the wrong quantum extremal surface to use here. And so using the wrong saddle gives the wrong answer. But the wrong answer for a given theory can, in fact, be information conservation. Not in the theory that we expect, but nonetheless, it is good to know that the mechanism that picks out the right quantum extremal surface really does know what it's doing. And that leads me to a few comments on this subject. So first, some takeaway. So using the correct quantum extremal surface for a given quantum theory of gravity, and that specification is in fact quite important, this is critical. We use the wrong one, we get the wrong answer. And so it's the mechanism that identifies the correct quantum extremal surface appears to be directly responsible for the unitary result in our calculation. Because if we had a mechanism that picked a different quantum extremal surface, it would give us the wrong answer. And indeed, in a non-unitary quantum theory of gravity, the mechanism that picks the quantum extremal surface would give us non-unitary answer. Now, in the replica wormhole papers, there was a Euclidean gravitational path integral calculation that justifies the page curve calculation in certain models. And so that means that we can compute a unitary page curve, again, just using semi-classical physics, as long as we're willing to also use the gravitational path integral in the saddle point approximation. And so it's looking like maybe the answer to this, understanding what is this mechanism that identifies the correct quantum extremal surface, is, of course, it seems to be rooted in the gravitational path integral. Now, including these Euclidean wormholes, these replica wormholes in the gravitational path integral appears to result in the cost of lack of factorization, which is suggestive of a potential interpretation, at least in the models that have been studied, of the gravitational path integral as some kind of an ensemble average. Now, ultimately, to address this issue, the gravitational path integral needs to stop being a black box. We need to have a better grasp on this thing. What entropy is it actually calculating in terms of, if you just compute minus trace rho log rho, what is rho that goes into this calculation? How does it know? How can we compute this entropy without using the gravitational path integral? And relatedly, this is related to the first point I was making. The quantum extremal surface prescription can give an answer which is both information loss and information conservation, depending on the dynamics of the theory and the fine-grained structure of the state. So we would like to know, what is the fine-grained structure of the state whose entropy is computed by the gravitational path integral, in particular, the part which is which receives contributions from replica wormholes. And more generally, what are some of the other fine-grained quantities, not just the von Neumann entropy or the purity or the Rennies, that are computed by the gravitational path integral? And what are they telling us about this mechanism that identifies the correct quantum extremal surface and how it's related to more fine-grained quantum gravity physics? And so I'm going to now spend a few minutes, I think my last 5 minutes, on a teaser trailer of an upcoming paper, which will hopefully be out within a couple of weeks, with Alex Maloney and Sebastian Fischetti. So as a general rule, again, we want to understand what's going on with the gravitational path integral better. We want to be able to compute extensive quantities. Not related to the gravitational path integral, that's just general rule. And this requires us to compute log z. In an ordinary quantum field theory, if you know log z with arbitrary sources turned on, you can calculate almost anything you want. Now, the inclusion of replica wormholes in the von Neumann entropy implies that here this calligraphic P refers to the path integral, P of B refers to the gravitational path integral with boundary conditions B. So PB to the n refers to a gravitational path integral with boundary conditions B to the n, so n copies of the boundary B. So the inclusion of replica wormholes implies that P of the path integral on n boundary is not the same as the path integral on one boundary raised to the power n. In particular, the Euclidean gravitational path integral, again, as I said before, appears to not be computing, at least in those certain models that have been studied, the exact partition function of a single theory, but rather potentially some ensemble average. So this means that it's possible, and as an aside, not only is it possible, it happens in real systems, that log of this average of z is not the same as the averaged logarithm. And so since what we really want is the ensemble average of log z, we would like to compute that. And to do so, using from the gravitational path integral, we can implement a replica trick. So this is analogous, but not the same. It's a distinct replica trick from the one that we normally use to calculate the Rennies. So just to make it quite clear how this is different from what we normally use to calculate the Rennies, this is an example of a Rennie entropy calculation. So here we have as von Neumann, this overbar simply indicates that this is an ensemble average that we're calculating. And so here we have these two logarithms. This is the replica trick for the Rennies. And we need an additional replica trick. So really this is a compounded two replica trick calculation. And here, so there's a replica trick that goes into both of these two logarithms. And so if you wanted to look at the replica structure, there would be n Rennie replicas, all of which are identified along some cut, and then you'd have m replicas of that. So you have n by m number of replicas, but the replicas are different. These are identified along some cut, and the m replicas are not. So far I haven't really said anything new in the sense that this type of thing has been known in, say, condensed matter systems for quite a while. What is the aspect which is interesting here, or novel in this case? So we can ask, essentially, is there a dominant contribution to more general extensive quantities from replica wormholes in any extensive quantity that we calculate from the ensemble average of log z, from log z as computed from the gravitational path integral? And sort of lightning result, and you'll have to wait more for the paper to come out, is that we find that in JT gravity and also in a variant of CGHS, there is a regime where replica wormholes do dominate log z as computed by the gravitational path integral using this replica trick. And we also find strong evidence for replica symmetry breaking in this regime. I should say this bears conceptual similarity to behavior that's exhibited by spin glasses, and that analogous behavior has been studied in certain limits of SYK doing a field theory analysis. Here's an example of one such paper that did that. So let me take the last minute or two to chat briefly about the road forward. So I think understanding the information paradox is of paramount importance for understanding space-time, the role of space-time in quantum gravity, space-time emergence in quantum gravity, and of course understanding paradoxes in general is a pretty good way to understand the theory. Now, holography provides a pretty tractable way of modeling black hole evaporation with semi-classical, or sometimes, as we have shown, purely classical tools. Now, the question of quantum gravity dynamics and the fine-grained structure of the state It's important, and it's not one that we have answered at this point. There are a lot of questions on what is actually going on at the non-perturbative level that sooner or later we are going to have to face. And we are at this point working on that. Now, in the same vein, some questions that we should really be trying to answer is, what does an observer outside the black hole actually measure? Is the path integral computing an ensemble average? What about, say, an n equals 4 superunion Mills? What does the presence of replica wormholes in the free energy mean? I haven't told you too much about what our calculations are like and what is their regime, so that's something that we'll have to wait until that paper comes out. And what does this mean for the path integral in higher dimensions? What's going on there? Is it an ensemble average? What is the free energy being dominated by replica wormholes in some regime mean? Does it extend to that regime, to those dimensions as well? It seems to me that the crux to all of this is unlocking the black box that is the gravitational path integral, and why it's so smart, why it knows so much, especially in higher dimensional gravity. That seems to me to be a very important question to answer. And so with that, I will thank you for your attention.
Thank you, Netta. So I'm going to unmute all briefly so that everyone can upload the speaker.
Okay.
I'm going to mute all. So I'm going to unmute Netta. So maybe you should unmute yourself. Okay. So I'm ready to take questions. The first question is from Samir Mathur. So I'm going to unmute him. Okay. Yeah, please.
Hi, Netta. Thanks for a very nice talk. Let me apologize for the question I'm asking because it sounds a little rude, but I really just want to understand what you're doing here. As somebody who's been reading these papers but not actually working in it, this is maybe a question from somebody slightly outside what you're doing. I'm just terribly worried that when people say they get the page curve by these methods, the argument looks circular to me. So you have a prescription for the QES, which seems to give you something that goes up and comes down. But on the other hand, when we look at the semi-classical approximation where we normally do Hawkings calculation, it just seems to go up. So normally, whenever we have found a conflict between what we saw from Hawkings calculation and the semi-classical approximation, we either have to show the semi-classical approximation is wrong, or we have a problem. So here, why wouldn't I just say, here's the semi-classical approximation. It seems to be working in your JT gravity plus scalar fields. And so the QES prescription is wrong. So if you turn it around and say, no, QES has to be right, so something new has to happen here with a black hole, it looks sort of circular to me. I would rather say that with just JT gravity plus scalar fields, the QES didn't work. And for something as simple as JT gravity plus scalar fields, I do think the information doesn't come out. I think it does stay trapped in, like in some talks I've heard from Maldacena, it gets trapped into a little remnant which may detach into a baby universe. And I don't really think you can learn anything from 2D gravity. So again, I apologize for the question, but I'd love to get your response on that.
No worries. Yeah, no, I think it's an excellent question, actually. So it's a bit of a loaded question, so I'm going to answer it in several pieces. And if I forget any of the pieces, please do remind me. So first, to address the question, actually, let me go up a few slides. This is going to take a long time. I'll answer it without going to a few slides up. So first of all, there is the question of what is the role of Hawkings calculation in all of this? And you're right. If you just do the Hawking calculation in JT gravity and the CFG, then we get what looks like information loss. You're also right that if you think of JT as a UV complete theory, then we also expect information loss. I would say we also don't expect that quantum extremal surfaces, that theory is properly holographic. So I would say we expect that in a holographic theory, of which JT is a low energy effective field theory, then we do have quantum extremal surfaces computing correctly the von Neumann entropy of that in that holographic field theory. So that is the short answer to what you first asked. But I do think it's important to identify something here, which you're correct that we have not identified, which is what is wrong with Hawking's calculation. If we want to say the quantum extremal surface calculation is the correct calculation for some holographic theory, which is a good UV completion of a low energy limit of JT, then we had better say what went wrong in Hawking's calculation. Now, if you want to do this Euclidean path integral calculation using the replica wormholes, you could say, well, a Hawking's calculation is analogous to not including the replica wormholes. But of course, Hawking didn't do a gravitational path integral calculation. He just straight up calculated the entropy. And so it's not clear, I would say at this stage, what is the point at which the Hawking calculation does not reflect the entropy of a unitary UV completion of JT gravity. So I think that is something important that we do need to investigate. However, I don't see the circular logic here, in the sense that, as I said before, you could imagine having multiple UV completions to JT gravity, some of which are non-unitarian. You have this baby universe, and the Hawking calculation was right, and some of which have a unitary UV completion, where the correct prescription is the holographic one, which is the quantum extremal surface calculation. Now, I may have missed one or two of your questions, so please remind me if I did.
Yeah. So I'd like to allow one iteration. So if Samir has one more point to make or two, please.
Okay, yeah, so maybe I could follow up with the thing you said about the how we do the replica calculation. I found that a little circular as well for the following reason. So I'd like to get your response on that. Suppose somebody did a Gibbons-Hawking calculation, which is the Euclidean amplitude, and they did a disk calculation, but of course you should add handles to it. You should do whatever the Euclidean gravity wants, but I think it will always give you a finite answer. On the other hand, when you look at the Lorentzian section, we know we can make the bags of gold slices with infinite amount of entanglement with the outside, and the Hawking evaporation process of a black hole, which is repeatedly fed and evaporated, in fact, automatically creates this divergent amount of entanglement entropy. So in fact, the puzzle is the fact that the Gibbons-Hawking answer is finite, and the actual Lorentzian section gives a divergent answer. So if somebody does a Gibbons-Hawking kind of calculation, in this case, not just for the entropy, but for an entanglement, but it's similar in spirit, it looks like to me, and gets a finite answer, it's actually not really addressing the question. It would be as difficult for me as saying the Gibbons-Hawking gave a finite answer, even including handles. And so there is no puzzle. The puzzle is the fact that Gibbons-Hawking gives a finite answer, while the Lorentzian section actually gives a slice on which you can put unbounded entanglement. So in fact, I'm glad you mentioned the replica wormhole kind of thing, but really my question is similar for that as well.
Okay, I guess I'm not 100% sure what exactly you're asking. I know, Hiroshi, you probably want to move on to other questions, and I'm afraid I'm not understanding the question. So I could either ask for a clarification, or we could take it offline. It's up to our moderator.
Let me make one more clarification. Since there is going to be the panel discussion on the last day, yes. You can have more discussion, but maybe if Samir can very briefly phrase a question in maybe slightly different way. So sure. We could try one more iteration.
Sorry, Samir.
Yeah, okay, let me do that. So I was just saying that we know the Gibbons-Hawking entropy is finite. Yeah. And if you include handles, I think it remains finite. So just allow you to include all the handles. On the other hand, there's an infinite entropy bags of gold slice in the Lorentzian section. So the mismatch between the Lorentzian divergence and the Euclidean finiteness is one way of stating the information paradox. So I was just saying that when people show me all these replica calculations, they are for the Euclidean answer. And if you analytically continue them, or whatever you can get out of the Gibbons-Hawking kind of calculation will always be finite. And if you present that to me as an evidence that something has been learned about the page curve or about the information puzzle, I would say, no, the finiteness of that was the puzzle, because the Lorentzian section doesn't agree with that. And the mismatch, in fact, is the puzzle. So showing me again the Gibbons-Hawking is sort of not helping me.
I think I understand the question now. I think I actually agree with you. I think that this is why I sort of keep on harping on the point that understanding what is why this calculation, this replica wormhole calculation, where it's coming from in quantum gravity, that's what's really is the critical aspect here. That's the crux of it. Because I agree with you that we haven't resolved the information paradox here. I think that's quite clear. There's still a question, there's still a paradox. I think what we have identified is another way, yet another way, in which the gravitational path integral seems to know something that should really be the purview of UV non-perturbative quantum gravity. And so we're essentially going about different ways of trying to extract that information and how that information gets there, what is to unlock the black box that is the gravitational path integral.
Okay, thank you for your patience. Yes, we
Okay,
can do.
Thank you. So let's move on to the next question from Sandeep. So I just unmuted him. Let's see. He should be unmuted. Can the organization team? Oh yeah, he's unmuted. Good.
Can you hear me now, Hiroshi?
Yes, I can hear you very well.
Thank you. Thank you for this opportunity to ask the question, and thanks, Netta. So I want to ask you something which I think sort of connects to what Samir is saying, but mine might be a little simpler, which is the following. You know, if you think about Hawking's calculation, one way to say why he gets information loss is if you include the contribution of the entanglement of, say, scalar fields on a slice, spatial slice, which cuts across the horizon. This entanglement, of course, diverges in 2 dimensions. It goes logarithmically with the cutoff, as you know. And then if you look at the system as it evolves, the effective cutoff becomes smaller and smaller. And that's where the seeming loss of information comes from. The entanglement outside just seems to grow and grow. What I want to ask you is this: if you are finding that information is not lost through your Euclidean replica trick calculation, is it because in some sense, if you were to think about it in a Lorentzian way, there is a minimum size that cutoff can take? And do you think if one thought about the fact that in any kind of dual theory, say in higher dimensions at least, you work at large but finite n, with n going like, you know, 1 upon g Newton, or n to some power going like 1 over g Newton, it's the finiteness of n ultimately which might be responsible for this cutoff being finite. I'm not sure I could put it accurately, but clearly enough, but just wanted to ask you.
So I suppose that traditionally, I think of the Hawking calculation as giving information loss more because you end up with, after evaporation, you end up with a mixed state. But you're right that you don't have to necessarily do this analysis to endpoint. You could already look at things at late times. Ultimately, I suppose it must be true that the finite n is really the critical aspect of this problem, and the fact that we have some UV completion, some UV unitary quantum theory of gravity that's implementing this, which is valid at finite n, which is really what's going on. I don't know of a way of, and I might be wrong about this, maybe some of the folks who wrote the replica wormhole papers can chime in on this, but I don't know of a way of seeing that in the replica wormhole calculations. I don't know how you would go about seeing that. There's also the fact that those models are somewhat specific in particular examples, and I will think that qualitatively speaking, it probably generalizes. I think the details might matter from model to model.
Okay, thank you.
Okay, I'd like to take one more question from Gurakshmi Subramani.
Yeah. Thanks for the nice talk. Thanks for the nice talk. So so you were showing some of the figures that involve this gamma and gamma prime, which are like quantum extremal surfaces that we are selecting as the black hole evolves in time, right?
Let me go there.
Okay, right. So we said that the island that is in between this gamma prime and gamma must be due to the quantum error corrections. So could it be a case that, so we were also saying that the Hawkings calculation might have selected the other, gamma instead of gamma prime, due to which there was information loss. Could it be a case that Hawkings calculation didn't even involve this kind of evolution at all? Like, so, the change of gamma to gamma prime itself is not being involved?
So certainly Hawking did not think of ER equals EPR, right? So the model here, which we're saying that the Hawking calculation is analogous to always picking the gammas, is simply a way of trying to understand what is the so let me actually rephrase this and say we want to really begin to start really resolving the information paradox. We're going to have to ask the question of where did Hawking go wrong? And so in this model, we could say an analogous calculation to Hawking's calculation, at least a calculation that gives the same answer, is the one that always picks gamma instead of having a switch over eventually to gamma prime. So if we understand better how that maps to Hawking's actual calculation, which is to say the calculation that actually computes minus trace rho log rho, then we would be in better shape to understand the difference between how our calculation would map to something like minus trace rho log rho. Does that sort of answer your question?
Yeah, sure. So so the small clarification about this is, so if the black hole evolves in such a way that there is no change, there's no change in the quantum extremal surfaces, would that be something similar to what Hawking calculated? That's
well, there should be a change because Hawking's calculation shows an irreversible increase in entropy. So if you wanted a model where the entropy somehow where the extremal surface somehow doesn't change, I think you actually would have to keep on pumping energy into the system in some way, because normally you would expect that the black hole will shrink as it evaporates.
Right, Ari. Okay, thank you. Thanks for the talk.
Thank you. Thank you. And thank you, Netta, for the talk. And I'd like to thank the two speakers of this session. So for those of you who came late to this session, Jeff made an announcement about breakout room after this. So maybe Jeff wants to say a few words on that.